detail was given to them. We didn't tell them how rigid we wanted them to be. We didn't tell them how thick we wanted the boards to be. We didn't tell them at which temperatures they could operate. We just gave them basic specifications, and they were to meet those in order to produce boards like this. And overall, all the data that I took and all of the results that I gathered were used to publish an internal paper that was submitted into the group. And then the group, the group leader, York, used those results, submitted them into a referee paper to an Atlas committee to determine whether they would continue the work on their design or not. And so far, we've gotten good results, and they have been allowed to continue the work on Archimedes chambers. So other work that I did while at CERN was do data quality shifts in the Atlas control room, which took 8 hours long. Do test beam shifts at the Previsson site with our chambers, which were also 8-hour-long shifts. Go to meetings and present my results to the group. Work on a 1x1 meter detector that we tested with cosmic rays at the time. Work on building the smaller chambers. Train new students. And attend summer student lecture series at CERN so I could enrich my education in particle physics. Yes?
What kind of fashion statement are you making there on the upper left?
Upper left? Here?
Yeah.
Oh, we're wearing clean suits right there. And I'm just looking at the camera to show that I'm coming out of there. But yes, in that room, you gotta make sure you don't shed any materials from your clothes or skin or anything like that. You're clean. Yes. Also, I got to experience the diverse culture of Geneva and the surrounding countries in Switzerland, near Switzerland. Thank you.
Questions for Simon?
Simon,
Yes.
will all the boards have to be tested if they can be used? Or
Yes.
just every single piece?
Every single board was tested. So I had a total of 17 boards, I believe, and every single one of them I needed to test the pitch of them and the measurements for the fiducial marks and copper strips. This took a very long time. I had 8-hour days in which I would go to work in the lab for the entire day. However, the weekends were for me, so I did not do that. Any other questions? No? Okay, I'll let my colleague Arya talk.
Alright, hi everyone, thank you for being here. My name is Arya Afshari. I'm a master's student here at Fresno State. So this is a continuation research from what I started last summer of 2011 to this summer of 2012, and it's still ongoing. So I was working with simulations of Atlas data using the old event generators and new event generators, which I'll get into more detail. So the motivation and the reason why I was working with simulations is because the beam energy of the LHC was upgraded from 7 teraelectron volts to 8 teraelectron volts. And that requires new simulations to make sure that everything's running properly. And those event generators, I compared the old event generator Pythia 6 to the new one Pythia 8. And also within the event generators, there's these things called parton distribution functions, which I'll get into more detail about. That is, I compared the new ones to the old ones. So to analyze data from the detectors, or in my case, simulation, we needed several tools. First of all, there's LX Plus, and what that is, it's a computer network where the physicists, they put their data onto the network, and other physicists can take it off and analyze it, and also to submit those Monte Carlo simulations, those event generators, to be completed, and then when they're completed, you could extract it from LX Plus. And the next two kind of go hand in hand. Root is a software package that analyzes high energy physics data, and it's written in C++, so when analyzing data, you have to write your code in C++. And Root was developed specifically for high energy physics, and it's good for when there's a lot of data, so you can organize your data and extract what you need. So the Monte Carlo simulations are basically when you don't have a definite answer for a problem you're working on. These simulations, they give you multiple entries being many thousands of entries for what you're looking for. So the result is what event is more likely to happen. event generator to the new Pythia 8 generator, where Pythia 8 is written in C++. So the parton distribution functions within these event generators, they tell you how the partons in the protons interact. Partons are basically the quarks and the gluons in these protons and neutrons, in these particles. So protons and neutrons are basically bags of quarks. When you're colliding them, you have all of these particles coming out. The PDFs, the parton distribution functions, tell you how these quarks interact and how they spew out new particles. So the PDFs I was comparing were the pre-existing CTEC, and then comparing that to the new MRST and MSTW. So this picture on the left is a proton. It's composed of 2 up quarks and a down quark. And then on the right is a neutron that has 1 up quark and 2 down quarks. Alright, so when we collide these particles, the spray of particles coming out is called a jet. So when you're looking at data and you're analyzing your data, there's certain things you need to look for in these jets, and we characterize the jets a certain way so we know what we're looking at. There's the transverse momentum, the invariant mass, the pseudo-rapidity, and the azimuthal angle. So the transverse momentum is the momentum in the perpendicular direction from the beam. So if we have a proton coming in from the left and a proton coming in from the right, and they collide at this collision point in the center, the transverse momentum is all the momentum that comes out perpendicular to the beam. So the picture on the right, if we have a proton and an antiproton colliding, the interaction point is here in the center. Whatever's in this XY plane is going to be the transverse momentum. The momentum in that XY plane is the transverse momentum. And then there's the pseudo-rapidity, or the eta, and that's basically the perpendicular direction from the beam axis. If the beam axis is this way, so the protons are flying left and right along the beam axis, the eta value is perpendicular to that direction. It's actually a function of theta, which is along the beam axis, so it's easier to work with the eta value in particle physics. Alright, and then there's the azimuthal angle. That's the angle around the beam axis. So in this picture, we have the protons coming at you in this blue dot or away from you. The phi angle is the angle around the axis that our jets come out at, or in this case, the transverse momentum in the picture. The invariant mass of a jet is basically the particle we're looking at when it decays. It has a certain mass before it decays. And the particle I was looking at decays into 2 quarks, and then those 2 quarks recombine with other quarks, and then we make a cone or a jet around all of these new particles coming out, and that jet is going to have a mass. So we take the 2 most energetic jets, and we add their masses, and we should get the mass of the original particle before it decayed. Alright, so the way pseudo-rapidity relates to azimuthal angle, we call this eta phi space, where this axis here is the eta value, this axis here is the phi value, and the vertical axis is the transverse momentum. So if we consider this eta phi space, this angle is eta, this angle is phi. If we wrap this around the beam, so now the particles are going through the beam, or through this cylinder, the 2 most energetic jets come out back to back. So the leading jet comes out on top, and the secondary leading jet comes out in the bottom. So they're 180 degrees apart. Alright, so this is an actual dijet event in Atlas data. This data is from 2008. You can see that it's actually at lower energy, at 2.36 TeV. Now we're currently at 8 TeV. So this is just showing in the eta phi space, we have two jets, the leading jet and then the secondary leading jet. So when I was analyzing my simulated data, I would take it, for the invariant mass, I wanted to see what the particle I was detecting it decayed into. So I got the invariant mass of those 2 jets, and the peak is at 1000 GeV. So this graph shows that the particle, its original mass was at 1000 GeV, and also what I said before, how I was comparing Pythia 6 to Pythia 8. So the darker line is Pythia 6 using the CTEC PDF, and then the red line is Pythia 8 using CTEC. So I use the same PDF and just compare the different event generator. So you can see very little difference between these two lines, and the relative difference is plotted on the bottom. Here they're very close to 0. So then, now that I know Pythia 8 and Pythia 6 are very similar, I compared the different parton distribution functions, the different PDFs. So I had CTEC compared to MRST, and these have very small differences. And then MRST compared to MSTW, and these also have very small differences. So then I compared a few of those different jet characteristics I was talking about. So the transverse momentum, this is again for Pythia 6 compared to Pythia 8, using the same PDF. And a relative difference, it shows that most of it is close to 0 in the regions of interest. So, same transverse momentum. Now we're in the Pythia 8 event generator, but I use CTEC compared to MRST, and then MRST compared to the MSTW PDFs. So here's a few of the other jet characteristics I talked about. There's the eta value. We see that most of these, most of the particles within that jet came out at the eta value of 0, which means it's perpendicular to the jet. And also, I have the eta of the leading jet. This is, or both jets combined. This is the eta of the leading jet. This is the eta of both jets. And then the phi angle, which is the angle around the beam axis that I was talking about. So, from all of this, we saw that those two event generators, since we wanted to upgrade to Pythia 8, it uses C++, and it contains some more new physics, so it's a valid upgrade. And then the parameters vary only slightly, and those small differences are okay because an event generator, a Monte Carlo simulator, is basically giving you various outputs. So they're gonna have some small fluctuations, which are okay. And then the comparison of those PDFs, MSTW and MRST, the new ones compared to the old ones, those also had small differences, but again, those are due to the event generators. And what I'm going to be doing next is there's new parameters I'm going to be looking for. So still using the Monte Carlo simulations, but looking at these new parameters. And also while at CERN, I covered 3 data quality shifts, and like Simon said, we're basically monitoring the quality of the data detected by the Atlas detector. So this is my last slide, and these are just some pictures from around Geneva. Most notably is this one, where it's the astronauts from the second to last mission to the International Space Station by the space shuttle. So 3 of them are American, and 2 of them are, one is French, one is Italian, and they're with the general director of CERN, Ralph Hewer. So they came and talked about the mission they did. And also on the far right, this is Hope Solo. If you guys don't know who she is, she's the goalkeeper for the U.S. women's football team. They won the Olympics in the summer. So it was a very productive and interesting summer for me. Thank you guys for your time. Oh, I just like sea manatees. So it's not from. I don't think the lake has manatees. Yeah.
What kind of operating system do you guys use? Linux or operating system for the computers?
Yeah, it's all run in Linux.
So the whole facility, pretty much?
Well, you could use your own operating system, like Windows, or I use Tiger for my Mac. But Linux is what you do, like what I was running my group in Linux terminal.
Alright, good afternoon everyone. I'm Navid, and I'm going to talk about the research that I did over the past 2 summers. So, summer of 2011, I was at CERN, Switzerland with these guys, but last summer I went to Daisy, which is in Hamburg, Germany, and I continued my research over there. So my project involved improving simulations in order to look for new physics at the Atlas detector. So just a quick overview. First I will talk about hydrogen physics and the main questions in hydrogen physics and how the standard model answers these questions. And then I will talk about searches for new physics and how we can use a contact interaction model, which is what I worked on, to look for new physics. And my project involved 2 software packages that were called AmpliGrid and NLOJet. And these are packages that have been developed by my pretty much search for new physics. So in hydrogen physics, the question that we try to answer is try to figure out what matter is really made out of. And this is a really big question that people have been asking for thousands of years. And for the longest time, people thought that everything is made out of this indivisible stuff that they call atom. But then we figured out that that the atom is made out of electrons which orbit the nucleus, and the nucleus turned out to be made out of protons and neutrons. And then those turned out to be quarks, made out of quarks. So now we think that everything is made out of quarks and electrons, or at least we think that we know. And it sounds pretty simple, but it's actually not. So this is a Lagrangian that's required to explain all these interactions between the quarks and gluons. So the reason that this is so complicated is because this is part of the standard model, which describes 3 of the 4 fundamental forces that we know of. So those forces are electromagnetic force, the weak force, and also the strong nuclear force. So the strong nuclear force is described by QCD, or quantum chromodynamics, which is part of what I'll also talk about. So the impressive thing about the standard model is that it has never been wrong. So there's never been a prediction by standard model which was not observed or which was like disproven. And that's really impressive considering how complicated this whole thing is. But even though it's never been wrong, that doesn't really mean that it explains everything, because it does not predict everything. Actually, there's many problems that we still can't figure out. For example, the standard model doesn't explain why there are 3 generations of these quarks and leptons. It also doesn't explain most of our universe, which is dark matter and dark energy. That's actually 96% of the universe. And gravity doesn't even fit in this whole picture at all. And also there's a problem with asymmetry between matter and antimatter, and we don't know why there's more matter than antimatter in the universe. And we also don't know why the different forces have different strengths. So these are all really big questions that we still don't have an answer to. And this is why we believe that there has to be some other additional new physics that we still haven't discovered yet. And we should be able to see signs of this new physics at higher energies. So there's a lot of theories that explain or try to explain these new physics. Some of them include things like higher spatial dimensions or supersymmetry or string theory. And there's probably more of these theories than there's people in this room. So it's really hard finding or figuring out which one of these theories could be the correct one. But before we start to look for new physics, we have to understand QCD or quantum chromodynamics really well. And the reason for that is because QCD is the dominant process at the LHC. And if we don't really understand this well, then we can't really move on to the next step. So again, QCD describes a strong interaction between quarks and the gluons, which are what protons and neutrons are made out of. And it's also the force that keeps the protons inside the atom together. So if you think about it, inside the atom we have 2 protons which are positively charged. So these guys really hate each other and they want to get away from each other, but the strong force is what keeps them together. So the reason that looking for new physics is so complicated is because at least with QCD, we kind of have an understanding of how these quarks and gluons interact with each other. But the new physics that we want to look at, we really have no idea what could be there, So there's a lot of possibilities. So the best way to look for them is to try to find a model-independent way to do this. And this is why contact interaction is useful, because we can approximate the new physics as this contact interaction. So I'll explain what I mean by that. So contact interaction is kind of a point-like interaction. So what that means is that we really don't know what the interaction is from, but we just assume that there's some sort of interaction going on in addition to the QCD interaction that quarks have with gluons. So this doesn't really tell us anything about possible structure of the quarks or what the new physics could be like, but it just tells us that there has to be some sort of scale or energy scale that we call the compositeness scale, or lambda, at which this new interaction becomes dominant or becomes visible. So what that means is that if you look at the quark, let's say, at energy levels lower than this lambda scale, then the quark should look like a point particle that we think it is. But if we go to higher energies and look deeper inside the quark at energies higher than the lambda, then we might be able to see a certain structure in the quark. So that's what we we try to do. And the best way to look for signs of this contact interaction is to look at the jet cross section. So jets, as Arya explained it, are particles or a bunch of the particles that are formed together after a collision. And these particles or these jets, they're spewed out in every direction. So we can also think of the cross section as like an area that contains these cones of jets. And the cross section is actually determined by the underlying physics that's going on. So by knowing the physics that's going on, we can calculate the cross section and then compare that to the actual data. And this is great because we can calculate the cross section using only QCD and get a cross section out. And then we can also do the same thing using QCD and this contact interaction, and then compare these two cross sections and compare them to data and see which one matches the data better. And there's actually many different ways to calculate the cross section. The most common way is to use PTI. So this is the most common event generator. And so we can use PTI, but the problem is PTI is kind of slow, it's CPU intensive, and it's also really hard to modify, and it's not that flexible. So that's why there's other software packages that people have been developing, like AppleGrid and AnaloJet, which my supervisor at CERN developed. And these software packages, they don't do everything that PTI does, but when it comes to cross-section, they're a lot easier to deal with than PTI. But then these aren't fully developed, so part of my project was to develop these fully and also make sure that all the calculations match with PTI. I also added the contact interaction contribution to these software packages, and also added them or extend them further to calculate new observables which PTI doesn't calculate. So the first thing that I had to do was to compare our calculation using these packages with calculation of PTI. And for that, so we have just a single jet cross section as a function of transverse momentum, and the blue line is the PTI calculation, and the black line is the Applegraph calculation. And you can see that they match very well. And the bottom graph is the ratio between the two, and you can see that it's like a flat one. So this is actually what I did during the first summer, or summer of 2011 at CERN. And then I tried to match these three calculations at the level of contact interaction, because this is just QCD, but we couldn't get the contact interactions of AppleGrid and PTI to match. So this summer, actually, I finally got to match those two, and I got something like this. So here you can see that again, the blue line is the PTI and the black line is AppleGrid, and this is for a contact interaction with a lambda or compositeness scale of 1000 GeV. And you can see that. So going back to this graph, so here on the top, you can see the graph kind of goes down at higher energy, so that means that there's less interactions going on at higher energies. But for contact interaction, you can see that something new starts to happen at higher energy. So that's the effect of the contact interaction, and that's a deviation from QCD. So again, here the ratio is 1, which means that our calculation at level of contact interaction also match PTI. So now I extended these softwares even more, and we calculate new observables, which PTI doesn't calculate. So we couldn't really compare these next ones to PTI. But here, these are jet cross section as a function of invariant mass. So this is actually for dijet. So the reason that we're analyzing these ones is because here you can see that the contact interaction becomes a lot more dominant. So this means that we might have a better chance of looking at this type of graph in order to look for new physics. So the two graphs are just the cross section at different regions. So the top one, so these two are the central region of the detector, and the bottom one is the forward region. And the black lines are QCD prediction, and the blue line is contact interaction. So again, you can see that the deviation from the sound model is huge. But this actually is kind of an exaggeration, because this is with a lambda of 1000 GeV, which is not really realistic. So these are just like similar graphs, but with some additional lambda values. So here you can see that as at 10 TeV or 10,000 GeV. So that means as far as we can see, we can't see any signs of compositeness or any structure of the quartz. But with this type of analysis, we hope to kind of lower this upper bound and maybe increase it to 15 TeV. So that's what the Alice group that I was working with are working on right now. So they're using the graphs that I created and all these calculations in order to analyze the data more. So just as a summary, I added contact interaction to these software packages, and I also calculated